In the following video, a 24 GHz and an 80 GHz FMCW radar level transmitter are compared based on practical applications. The advantages and similarities of these two devices will be shown and conclusions presented. A metallic sphere represents a conceivably weak reflector, since only a small part of the radiated signal is reflected back in the direction of the antenna. Thus, a sphere can be used to simulate reflections on products with a low dielectric constant, the so-called DK value. First, the metallic ball sphere is inserted under the 24 GHz device. In the spectrum recording, the reflection on the spherical surface is clearly recognizable. Now, the ball sphere is placed under the 80 GHz radar transmitter. Here again, the reflection of the sphere is immediately visible. Since both radar devices are FMCW systems, the devices have comparable dynamics as expected. The reflection on the spherical surface corresponds to a DK value of approximately 1.2 and is clearly recognizable with the 24 GHz as well as with the 80 GHz system. The radiation pattern of a radar system results from the combination of the frequency and the antenna diameter. In general, the following applies. With the same antenna diameter, the beam angle decreases proportionally when increasing the frequency. At the same frequency, the beam angle decreases proportionally when increasing the antenna diameter. The illuminated circles illustrate the areas detected by the respective radar system on the product surface. It should be noted that radar beams spread out conically from the antenna. For the selected system configuration, 24 GHz with an 80 mm horn antenna and 80 GHz with a 40 mm lens antenna. These areas are approximately identical. In this comparison, the radar beam can be demonstrated by using metal rings. In both systems, the radar beam travels through the ring opening. As a result, the rings are hardly visible in the reception signal. If the ring opening is reduced, the radar beam hits the metal surface and the ring is clearly visible in the received radar signal. If such a disturbance is caused, for example, by installations in tanks, there are two possibilities for optimization. Firstly, the disturbance can be hidden by recording an empty spectrum. For this purpose, the received radar signal of the empty tank is recorded and stored into the memory of the radar device, and then subtracted from each subsequent measurement. Second, the use of a large antenna can reduce the beam angle. This results in the following advantages. The radar beam angle no longer touches the ring surface. The complete energy radar signal is available for surface detection. Even with the 24 GHz system, an increase in the antenna diameter would achieve a similar effect, but a significantly larger antenna would be necessary. The advantages of a flush-mounted lens antenna are immediately apparent. Lens antennas do not protrude into the tank and thus allow an almost complete filling of the tank. Using horn antennas means that they protrude from mounting nozzles. Lens antennas, however, can be easily placed on nozzles, as shown in the example of a 50 mm nozzle in combination with the 40 mm lens antenna. A disturbance signal at the nozzle end, as it is usual at 24 GHz, does not occur. Thus, filling is possible up to the lower edge of the nozzle. The combination of a 70mm lens antenna with an 80mm nozzle provides, of course, identical good results. In the case of plastic containers, it is also possible to realize the filling level measurement without modification of a tank through the container casing. The plastic plate inserted here simulates the container cover. Behind the reflection of the plastic plate, the reflection of the water surface in the spectrum is clearly visible. The reflection of the plastic plate can be minimized by an oblique positioning, simulating, for example, an oblique tank roof. As expected, the 24 GHz system also shows a comparable behavior. Here also, the reflection on the surface of the water is clearly visible. As expected, the inclined position of the plastic plate also reduces the reflection on the simulated tank roof. Both radar systems are not only suitable for the measurement of low reflective products, but are also able to measure through tank walls or tank roofs made of plastic. Such applications are found, for example, in bioenergy plants, in the level measurement in the fermenter, where the measurement typically takes place through a plastic foil. Besides measuring through non-conductive tank walls, it is also possible to measure through metallic grids and sieves. In order to show this, first a coarse grid is placed on the lower of the two rings. In the signal spectrum, the interference in the reception signal is weakly recognizable, but has no influence on the reliable detection of the product surface. Even a narrow closed mesh grid does not cause any problems during the measurement. The disturbance in the radar beam angle is also visible that does not affect the actual measured value. Even if the amplitude of the disturbing echo caused by the grid exceeds the amplitude of the reflection of the product surface, a reliable measurement can be ensured by increasing the block distance or recording an empty spectrum. The bandwidth of a radar system determines, among other things, the distance resolution of the system. Clearly, this means the higher the signal bandwidth, the better the distinction of two mutually close reflections, and thus, for example, the separation of the product surface from interference reflections. By observing the reflections on a double plastic plate, this effect can be demonstrated. For this purpose, a double plastic plate is first placed in the radar beam of the 24 GHz device. However, with a signal bandwidth of 2 GHz, no clear separation of the two reflections is possible. The 80 GHz system, with a signal bandwidth of 4 GHz, allows, however, a clear separation compared to the 24 GHz system. Finally, two application examples with real products are considered: plastic granules and wood chips. The great dynamics of FMCW systems allows reliable detection of very weak reflective products, such as plastic granules. Plastic granules have an effective decay value of approximately 1.6 and can be clearly detected with both systems. Seen here with the 80 GHz system and also with the 24 GHz system. A much greater challenge is the detection of the surface of dry wood chips. The 24 GHz device reaches its limits. The radar beam penetrates the product and is not sufficiently reflected by the product surface. Thus, a measurement is not possible. The 80 GHz system is superior to the 24 GHz system for this application, which comes from the more focused radar beam. Therefore, the wood chips are clearly detected with the 80 GHz. The cleaning of tanks by means of spray balls is a common method in the food industry. This is now demonstrated by means of a water jet, which is brought into the radar beam of the two devices. Again, the high dynamics of the FMCW radar systems prove to be advantageous since it allows measurement even during the cleaning operation. Both systems reliably detect the product surface. The water jets have no significant influence on the measurement. The 80 GHz technology opens further areas of applications for radar level measurement systems thanks to small antennas and precise focusing at the same time. In general, however, the optimal frequency range must be used for each application. Drexelbrook offers a complete radar portfolio based on the FMCW radar technology. Our reliable level measurement devices have been installed in more than 100,000 systems worldwide. They are proven over years of extreme conditions and trusted by some of the largest companies in the world.